now that we have seen how to use these properties of logarithms, let's take that information and let's work on evaluating some logarithms, some expressions. Starting with this. So if I ask you to evaluate log of 100,000. So keep in mind that when I'm using just regular log, that's understood to have a base of 10. And remember the way that logarithms work is we're trying to figure out, okay, my base is 10. 10 to what power gives me what's on the inside of the logarithm? Okay, well, for powers of 10, it's pretty simple. You just count the number of zeros that we have. So we have 5 zeros, and so this is going to equal just 5. Again, not a whole lot going on there, just like if I were to have, what's log of 100? Again, by having the common log, it's understood to be a base of 10. What's the power of 10 that gives me 100? And the answer is 2. Okay, again, not a whole lot going on there. Now, if I do this, if I say log of the 7th root of 1,000th, this one might be a little bit trickier, but if we break it down piece by piece, it's actually not that bad. So when I say break it down piece by piece, I mean this. If I didn't have the radical and I didn't have a fraction, and you had to think about just this piece right here, what is log of 1,000? Well, based on the 2 previous problems, you should say the answer is 3. Okay, so I can go ahead and write 3, but let's understand that's not all, though. So the 1,000 was in the denominator. So what power of 10 is going to lead you to 1,000 in the denominator? It's not just 3, but it would be -3, because remember, the answer to logarithms will be a power, and negative powers lead you to doing reciprocals, lead you to fractions. Okay, and how do I end up with an index of 7? Well, in a previous video, I said that the index becomes the denominator, and so this is the answer. So we saw something just a little while ago when I had log of the square root of c, and we were able to rewrite this as, well, before we did that, we said this is log of c to the 1/2, and then we use the properties of log to say 1/2 log of c. Well, similarly, if I have log of the 7th root of, let's say, c squared, I can rewrite that radical as it's still c squared, but that index becomes the denominator of the power. And then I'd be able to rewrite it in front like this. So that's really what I'm playing off of here whenever I write -3/7. Again, the answer to the log is the power. So what power of 10 would lead to a 7th root? That'd be a power that has 7 in the denominator. All right. If I have the natural log of e to the -8,923rd power. Now, we could try to be all cool and type this into our calculator, right? But I think it might give us an issue. Now, I could be wrong, but let me see. If I do the natural log of, so if I want e in the power, I'm going to go second natural log -8,923. It gives me an error. Okay, so it gives me an error with the domain. Basically, it's not liking that number that I have there, and it's running into an issue trying to evaluate that, because it's going to be a really, really, really tiny number. Now, even if I had gone in and done this, take off the negative, now it gives me a different kind of error. It says, oh, there's an overflow error. Basically, when you get an overflow error, that means that you're trying to have the calculator evaluate a number and it's too large for it to work with. It's just too big. But you know what? We've got properties of logarithms, and we can work this out. Because I know that the natural log really means log base e, so then of e to the negative 8,923 power. And we saw with the properties of logs that if the base of the log and the base of the exponential inside are the same, the answer will be simply the power. And that's all that it is. So if I had done natural log of e to the positive 8,923rd power, which my graphing calculator says can't do that, the number's too big, because the base of the natural log is the same as the base of the expression inside, e, the answer is just 8,923. So here's where the problem happens with the calculator. The calculator first is trying to figure out what is that number. And it's too big for the calculator to handle. There are limits to how large the numbers can be in the calculator. So that's where it runs into an issue. Not because it can't evaluate the natural log, it's because it can't evaluate e to that huge power. But the calculator is not using properties of logs. It doesn't recognize that they have the same base, and so you're just left with the power. But you know what? That's okay, because we are smart students, and we are paying attention. So if I have 7 raised to the log base 7 of the square root of 62. This is another one of those theorem on inverses problems, because the base of the exponential is 7, the base of the log is also 7, so since those guys are the same, your answer is just going to be the square root of 62. That's it. Done and done, right? And the next example is very similar to the last two. Log base 31 of 31 raised to the 18 pi. So again, the base of the log and the base of the exponential are the same. And we're left with just that power, which is 18 pi. Now, this might be something that can be done in the graphing calculator. Oh, but having the base of 31 is really kind of messy. Well, we could do change of base theorem on that. And we could say log of 31 raised to the 18 pi is second power. And we can divide this by log of 31. So again, that's an application of the change of base theorem, which says if you apply the same log to both the expression inside for the numerator part and for the expression, and for the base, that's going to be the same thing. Let's hit enter and see what it tells me. So it tells me, now this is only going to be an approximation because those decimals are really messy, 56.5487-ish, right? Well, let's check if I do 18 pi, I get the same answer. Now, I don't know about you, but I like that one because this answer is exact. And again, it's using the properties of logarithms, so it makes it super nice and easy, right? Now, I do like doing the change of base theorem, so let's take a break. We're going to come back and see how we can use that to easily simplify some other logarithmic